Welcome to class, everybody. Today we will be learning about number theory, okay? This is very basic number theory, and this is our schedule. First, we'll be covering prime and composite numbers, and then we'll go over scientific notation. And lastly, we'll go over rational and rational numbers. So that is our schedule for today. And first, I'm going to be going over prime numbers, okay? So the definition of prime numbers are numbers that are greater than 1 and only have two factors, 1 and the number itself, right? And some examples include 2, 3, 5, and 7, right? 2, the only factors of 2 are 2 and 1, right? Only factors of 3 are 3 and 1. And the only factors of 5 are 5 and 1. And all the factors of 7 are 7 and 1, okay? So now that I've gone over the definition, please try to think of some prime numbers of your own, okay? So please come up with a set of 3 prime numbers. So different from the example, please come up with 3 prime numbers. And don't use the ones in the example. Okay, so I'll give you some time. Just brainstorm some and put them in the chat, okay? After this warm-up, we'll be doing some practice problems. Okay. Good. Yes, a lot of prime numbers. Okay, very nice job. Yes, thank you for answering, and we'll move on. Okay. And let's do another warm-up question. Is 76 a prime number? Okay, another warm-up question. These are pretty easy and you should be able to do them well, okay? Is 76 a prime number? Please put your answers in the chat. Okay, no. Yes, correct. It is a factor of, it has factors of 2 and 38. Someone said that earlier, so good job. And with this question, you might notice that every even number, let's say, except for 2, every even number except for 2, let's say 4, 6, 8, or even 100, they are all not prime numbers, correct? They are all not prime numbers. For example, 4 is 2 times 2, right? And 6 is 3 times 2, okay? So remember this, all even numbers have a factor of 2 in some other number, so they are not prime numbers. And that is excluding 2 because 2 is very special among them. Okay? And does anybody want to take some notes on the definition of the prime numbers? Who wants to take notes on the definition? Okay. So no thank you. We'll move on then. So let's go over the definition of composite numbers now. Definition of composite numbers are positive numbers that can be formed by multiplying two smaller positive numbers other than 1 in the number itself. So basically the opposite of prime numbers, right? So examples are 6, 24, 900, 765. So let's do the same warm-up question, okay? Please brainstorm 3 to 4 composite numbers, okay? Please brainstorm 3 to 4 composite numbers and put your answer in the chat. Okay, so you'll start up with a little warm-up question. Okay, yes. Very good. Those are all composite numbers. Yes, thank you. And you must notice that all the even numbers excluding 2 are all composite numbers, right? So all the even numbers excluding 2, let's say 10, 54, 100, they're all composite numbers, okay? So, and then it's very easy to brainstorm a lot of composite numbers, right? You just have to make sure it's divisible by 2. And let's do another warm-up question. Is 3,657,356 a composite number? Okay, so please put your answers in the chat. Yes, okay, the answer is yes. So very good job. Okay, so now that I've gone over composite numbers and prime numbers, the definition, let's work on prime factorization, okay? So prime factorization. So what is prime factorization? Well, if you take a number, let's say 100, right? You can factor it into 50 and 2, right? They are both factors of 100, and the idea of prime factorization is factoring a number into only prime numbers. Okay? So how can you represent 8? How can you how can you represent 8 with only prime numbers? Okay? So what is the prime factorization of 8? Okay? 8 equals 2 times 2 times 2. And these 3 2s, 2 is a prime number, right? So 8 can be represented with 3 prime numbers. So 2 times 2 times 2, right? That equals 2 cubed. So that is the prime factorization of 8, okay? And now when you get into bigger numbers, let's say 1,000, okay? You can't just do it mentally anymore, right? So today I'm going to introduce 2 easy methods to do prime factorization. So the first one is the factor tree, okay? The factor tree. And to do the factor tree, and this takes up quite a lot of space. So let's say we're trying to find the prime factorization of 100, okay? And then, so you put 100 at the top, right? And what are 2 factors of 100, okay? So please put in the chat, what are 2 factors of 100. Okay, what are two factors? Okay, so someone said 50 times 2, right? 50 and 2 are two factors of 100. So what we need to do is put 50 on one side and 2 on the other. And 2, we have a prime number, right? 2 is a prime number. So we circle that and we don't go any farther from that because that is already a prime number. We don't need to mess with it anymore. So now let's go from 50. Okay, so name two factors of 50. Two factors of 50. Please put your answer in the chat. Okay? 25 and 2. Very good. Okay. So let's do that. 25 and 2 is another prime number, okay? So we circle that and we don't go from that anymore. And then we get 25. 25 is the square of 5, right? So we can just write 5 and 5 is a prime number. And here we have it, a prime factorization of 100, right? 5 times 5 times 2 times 2. And remember to simplify into 5 squared times 2 squared. Okay? And then now let's solve the prime factorization of 100 using the division method. So we'll get the same answer, but using a different method, okay? So same thing, we need to put 100 at the top, right? Okay? And let's we put it in this format, okay? This is like a box, right? Like a box. Put it in the box, and on the left side of this box, choose a factor. Choose a divisor of 100, okay? And it has to be a prime divisor, okay? It has to be a prime number. So the number on the left, right, it has to be a divisor of, or a factor of 100, and it has to be a prime number, okay? So let's start off with 2, right? 100 can be divided by 2, and 2 is a prime number, so it fits the requirements. So let's put 2 there. Then what is 100 divided by 2? It is 50, right? So we write 50 beneath it, put it in another box. Okay? And what is a prime factor of 50? So 50 can be divided by 2 again, because it is an even number, right? So we can put 2 again. And what is 50 divided by 2? Okay, so I've started the division method here. Can you guys finish it? Who can finish? Please try to finish this this problem using the division method. So let's start off with please find a divisor of 25 that is prime. Okay. 5. Yeah? 5. Okay. And then 25 divided by 5, you end up with 5, right? So you get these 4 prime numbers, and you can simplify to 5 squared times 2 squared, right? Okay, so there you have it. Okay, another method of solving prime factorization. So let's move on to scientific notation. Or do you guys want to take notes on this? Okay, I'll leave this slide up if you want to take a screenshot or a photo, and then you can take notes later. Okay, so is everybody done taking their screenshot? Okay, so now let's go to the scientific notation. Okay, so does anybody know what scientific notation is? Has anybody heard of scientific notation? Okay, so a lot of you have. So let's deepen your understanding now. Okay. And Anthony asked, what grade is this? Anthony, this is 7th grade curriculum, okay? And we're learning number theory. So now let's go over scientific notation. So scientific notation is written in this form. Okay, it's written in this form. And here C represents a number between 1 and 10, but not including 10, okay? C is a number between 1 and 10, but not including 10. Okay. And this exponent over here, okay? This exponent can't be 5 to the n. It can't be 3 to the n. It can't be that. It is always base 10. Okay, always base 10, okay? Okay, so that is basically a very basic structure of scientific notation, okay? And to simplify a number or put a number into scientific notation, this is what it looks like. So 120,000 equals 1.2 times 10 to the 5th. Okay, so let me show you step by step how we get that. Okay, so we have this number 120,000. So first we need C to be a number between 1 and 10, but not including 10, right? So is there a number, okay, in 120,000 that is between 1 and 10, okay? There is. If you look closely, we can separate this 12 here, and you can make that into a 1.12, right? Okay, so this number, let's say you had 545,000. You will have to include all the numbers that are not zeros into this box, and then you have to move the decimal point and turn this number 545 into a number that is between 1 and 10, right? You can move the decimal point right here. You get 5.45, right? So you turn this 12 into 1.2, we get C, right? Or whatever variable you want to be. So we have our 1.2, and then you have to multiply it by 10 to some unknown exponent, right? And now we're trying to find that exponent. Okay. So to find the exponent, the decimal point is here, right? So I'll show you a little trick. Decimal point is here. And how many places do you have to move it to the end of this number? Okay, so let's count. 1, 2, okay. 1, 2, oh, the zeros are too far apart. Okay. 1, 2, 3, 4, 5, right? 5 places we have to move for the decimal point to be at the back. And then that will be our exponent. Okay? That will be our exponent. So to clear your understanding, let's try another example. Okay? And let's use the example that I just gave earlier. 545,000. So please try to find the scientific notation of this number. Okay? So, and put it in the chat. Okay. Please find the scientific notation of this number, 545,000. Okay, so let me give you a small hint. So all the numbers that are not 0 are 545, right? And then please move the decimal point and turn this into a number that is between 1 and 10. Then you'll go from there. Okay, so this is usually the first step. So please try to solve this on your own. But if you don't know, then I'll show you later. Okay, I'll walk you through it later. So please put your answer in the chat box. Okay, so we have 5.45 multiplied to 10 to the power of 5. And we also have 5.45 multiplied by 10 to the power of 4. Okay, so I'm seeing mostly two different answers, okay, here. So are there any more answers? Are there any more answers? Okay, I'll give you a bit more time to try and solve. Okay. So let's try it now. Okay. Let me erase this box. There we go. So we have to turn 545 into a number between 1 and 10, but not including 10, right? So let's move the decimal point 2 places to the left. And we get 5.45, right? That is a number between 1 and 10, but not including 10, okay? And we get C, or X or Y, or whatever variable you want that to be. So we have part of it, and then we have to multiply by 10 to some unknown exponent, right? Now we're going to find that exponent. Remember that little trick that I taught you. See the decimal point right here? Move it to where it's at the end of the number. So let's see. 1, 2, 3, 4, 5. And how many places you moved will be the exponent. So the scientific notation of this number will be 5.45 times 10 to the 5th power. Okay? Does everybody understand? Okay, yes, good job to everyone. And let's move on to a practice question. So this practice question is, how do you write 450,000 in scientific notation? Okay, so this one I won't give you a hint. So this one, please try to do it on your own. Okay, so remember those helpful tips and tricks that I taught you when doing scientific notation, and also try to make use of this formula over here. Okay, so the scientific notation should be in this structure. Okay, it should be in this structure. Okay, so I'll give you some time to try and do this, and please put your answer in the chat. Okay. Okay. So there are two answers. I'm seeing 4.5 times 10 to the 5th, and I'm also seeing 4.5 times 10 to the 6th. And also, Abel, this class will be 1 hour. There's 30 more minutes. And Oscar said 4.5 times 15 to the 5th power. And the rest of the answers are pretty similar. So, is everybody ready? Does everybody have an answer? Ready? Okay. If you are ready, then I will walk you through it. So let's start. Okay, Oscar, you meant the... Okay. So let's write 450,000, and this is the these are the numbers that are not 0, okay? And can you turn this into a number that is between 1 and 10, right? How do you turn this into a number between 1 and 10? So you just move the decimal point over here to 4.5, okay? So you get 4.5, that will be C. And then that will be multiplied by 10 to an unknown exponent. Now we're going to find that exponent, okay? So remember that little trick. Find the decimal point, move it to the end of the number. So 1, 2, 3, or 5. 5 is how many places you moved it, and there you have it. It is 4.5 multiplied to 10 to the 5th power, okay? So that is how you find the scientific notation, okay? So a lot of you got the correct answer. So congratulations. And a lot of you are doing well. So let's move on to irrational and rational numbers. Okay. So now let's go over the definitions of irrational and rational numbers. So rational numbers are numbers that can be written in the fraction form p over q with a non-zero denominator, okay? So p has to be some sort of decimal or terminating decimal or integer, okay? And then q cannot be equal to 0, okay? So an example of a rational number would be 5 over 4. And 12 would also be a rational number because it can be written as 12 over 1. Okay, so those are examples of rational numbers. And let's go over some more complicated examples of rational numbers. So rational numbers, let's say you have this decimal 3.61, right? This is a terminating decimal, which means it stops, right? It stops at 3.61. It stops at this the hundredths place, 1, right? In some decimals, they go on forever, right? And say pi, right? 3.14159265358. It goes on forever in a random pattern, right? Okay, goes on in a random pattern. So that is not an example of a rational number because it cannot be written in this fraction form because p has to be a terminating decimal or an integer of some sort. Okay? But, however, let's say you have this number 0.16 with a repeating sign over the 6, okay? So this basically means this decimal is 0.16666 goes on forever, right? In that pattern, and the 6 is repeated. Is that a rational number? Yes, it is in fact a rational number. Now you might ask why. Pi is a decimal that goes on forever, right? And 0.16 with a repeating sign over the 6 is also a repeating decimal that goes on forever, right? So why is it a rational number? Well, 0.16, okay, the repeating sign over the 6 actually equals 1 over 6, right? And 1 over 6 is a fraction, and it meets the requirements of a rational number, right? So actually, these kinds of decimals are, in fact, rational numbers. Now, let's look at this. So, you might ask, are all repeating decimals that have a specific pattern like this rational numbers? The answer to that is yes, okay? So all decimals that are repeating, okay? So not like pi. Pi goes on forever in a random pattern, okay? So it goes on forever in a random pattern. You can't predict it. However, 0.16, it goes 0.16666, goes on forever with a 6, right? It's very predictable. 6 is predictable. Okay, so that is not a random pattern, as 6 is repeated. Or let's say you have 0.545 and repeating sign over the 545. Then it'll go on forever in this pattern. 0.545, 545, 545, 545. It'll go in that pattern, right? Okay, so it repeats on the 5, 4, and 5. Okay, so those kind of fractions, those repeating fractions that have a pattern, those are rational numbers, okay? And irrational numbers are just numbers that do not meet the requirements of a rational number, okay? So some examples are x. X is just a variable, right? You don't even know what it is. It does not have a value. Okay, you can denote x as anything, right? X could be 4, x could be 2. So that does not meet the requirements of a rational number, okay? Has to be an integer, has to be a number, can't be a variable. Another common example are imperfect square roots. Let's say square root of 2. Square root of 2, you don't know what that is, right? Okay, so that is not a perfect square. However, on the other hand, square root of 4 equals 2, right? So that is, in fact, a rational number, okay? So square root of 4, square root of 9, all those perfect square roots out there, those can be simplified to integers, and those are rational numbers, okay? So imperfect square roots like square root of 2, square root of 10, square root of 7, square root of 13, those are imperfect square roots, so they do not meet the requirements of a rational number. Another common example is pi, right? Pi, okay? So now that you know the definitions of the rational and rational numbers, let's do the same warm-up question. Please brainstorm types of irrational and rational numbers. So please brainstorm 3 to 5 irrational numbers, and please brainstorm 3 to 5 rational numbers, okay? Okay, so Ray Shan, okay, couldn't pi be written as 3.14159 divided by 1, right? So very, very good question. Okay, very good question. Because p has to be a terminating decimal. Can't be a random repeating decimal, okay? Can't be that. A terminating decimal means that it stops at some point. Let's say 10.25, right? It stops at the hundredths place at 5, right? But pi, that decimal goes on forever, right? So p can't be a decimal that repeats forever, okay? But 0.16, you might say, is also a repeating decimal, right? But 0.16 repeating can be simplified as 1/6. So that is a rational number, okay? So now let's brainstorm 3 to 5 irrational numbers and 3 to 5 rational numbers. Okay, so please separate them. Put them in different comments, or just name them each. Okay. So someone said 2/3, 5, and 4.53. Okay, very good. Nice job. Congratulations. And does anybody else have any more examples of rational numbers and irrational numbers? Okay, so I'll give you some time to brainstorm them. okay? 0.13, just 0.3, okay, sorry. That is a rational number. Very good, very good. And Carney said pi and the square root of 2. Very good. And Oscar says rational 4/8, 0.75, and then negative 0.5. Very, very good. Okay, so let's stop brainstorming and let's do some problems. Okay. So now let's go over some common rules of rational and irrational numbers. So you must know that rational multiplied by rational equals rational. Okay? So let's say a rational number is a over b, right? Okay, so this is where it gets a little bit hard. We're going to be using some algebra to prove some of these rules. Okay, so let's say a rational number is a over b, right? And to multiply that by another rational number, let's say it's m over n. Okay, so that is another rational number. And then the result will be obviously am over bn, right? Okay, so a and m will be integers or terminating decimals, right? So a multiplied by n will be a rational number. Okay, so both of them are either terminating decimals or integers. So when we're proving these rules, let's say a and m are both integers, okay? Let's say both of them are integers. And integers multiplied by integers are always integers, right? They're always integers, not something else, okay? Let's say b and n do not equal 0, okay? They do not equal 0, and they are also integers. And then what do we get? Rational over rational. And then we get another rational number, okay? So a and m and b and n are both integers, okay? So let's say they're both integers. And integers divided by integers is another integer, right? Or it could be a terminating decimal. And terminating decimals and integers are all rational numbers, correct? So that is how we prove that rational times rational equals irrational. Now, let's prove rational plus rational equals irrational. So let's use the same examples. A over b plus m over n. Okay? So let's see. Okay, so how do we make sure this is a rational? Okay? So we can't let's say a over b was 3 over 4, right? And m over n was 2 over 9, right? They don't have common denominators, right? They don't have common denominators. We can't just add them. Okay, we can't just add them. In multiplication, you can just multiply straight across. But now we have to find a common denominator. So now you have to multiply both of them. So we have to multiply a over b. We have to multiply both a and b by n. Okay, so let's multiply both a and b by n. So we get a n and then b n. And then the other side, let's multiply other side by b. Okay, so we get bn over bm. And what do we get? We get a common denominator of b times n, right? And then we can add them together. The top will be an plus bm over the common over bn. Okay. And now we proved it because a, remember where I said a will be an integer. Okay. B will also be an integer. The same with m and n, right? And integers multiplied by another integer plus another set. So integers plus integers will equal to integers. And then an integer over b over n, and b and n are also integers. And when they multiply, this is another integer. So basically, it'll just be an integer over an integer. Okay? And that will be rational. Okay? That will be rational. So does everybody understand? Okay? Does everybody understand? So integer over integer, this will be a rational number, and then this will also be a rational number. Okay? So that is how we prove that. Okay? Now we start working with rational numbers. So a rational times an irrational can be an irrational number. Okay, so irrational multiplied by rational equals irrational, but sometimes you don't know that, right? So how do you prove this? We prove this by assuming that irrational times rational actually equals rational. Okay, so let's assume that it actually equals rational. And if we prove that it is not rational, then we know it's the other way around, right? So if we prove that it's not rational, we know that it's irrational. So let's try to prove it's not rational, okay? So let's say a over b, that will be our rational number, okay? That will be our rational number. Then x will be our irrational number. Okay, there we go. So x is our irrational number, and a over b will be our rational, okay? And let's say that equals to m over n, because n over n will be another rational number, right? M over n is another rational number, and we're assuming that ab times a over b times x equals a rational number. So that's why it's supposed to equal to m over n. Okay, so remember when we studied algebra last year? How do we? So we want to get rid of this rational over here, okay? You have to get rid of that, okay? So let's do that. So let's multiply every term by b over a. Let's multiply every term by b over a. And then these will cancel out, right? These will cancel out. And then we also multiply x by b over a. So bx over a equals bm over am. So now we get this. Hey, now we get this after we multiplied every term by b over a. So we canceled out this rational number, and now we only have two numbers here. So remember, let's say b over a was 3 over 4, and then x was pi. X was pi. So b times x over a would actually be 3 pi divided by 4, right? 3 pi over 4. And then that is irrational, right? Because pi can't be on the top. If it's on the top, it wouldn't be a rational number. And then, however, b times n is an integer, and a over m, a times n, m is also an integer, so this would be rational. And this would be irrational. And somehow, this is very interesting. Okay, somehow we get irrational equals rational. How do we do that? So a rational number does not equal a rational number. So this big no-no. Okay? So this is unequal, okay? And that is how we prove that rational is incorrect. Okay? Okay. Oh yeah. Also, yes, I made a mistake here. It's a over n. A times n, okay? So thank you for correcting me. Okay. So now the last rule is a rational times an irrational can be both a rational number or an irrational number. So let's try to go for a rational number right now. So let's say square root of 2 is an irrational number times another irrational number. So when you multiply these two square roots together, they're the same, right? Be square root of 2 squared. And then, square root and square, that cancels out, obviously, right? And that would equal to 2. And 2 is actually a rational number. So that is how irrational times irrational can be a rational number. Now let's see. Okay, let's use the square root example. Square root of 2 times pi, which is another rational number. Okay? You can't figure that out, right? It'll still be a never-ending decimal with a random pattern, right? So this will be an irrational number. Okay? So those are two examples, okay? You can just prove this theory using two examples. So now let's start practicing. Okay? So number 1 is list 3 different rational numbers. Okay? So list 3 different rational numbers. Please list 3 different rational numbers, okay? In the chat, please. Steven says rational, -6, 5, and 8. Very good job. And Carney says 3, 1.5, and 1/4. Okay, and there are many other answers. Very nice job, everybody. These are all rational numbers. Super job. Okay, so congratulations on getting it all correct. Okay, so let me just come up with a few of my own. Let's say -29, square root of 4, and 9. Okay, those are 3 rational numbers. And okay, this is number 2. Okay, so using the rules that I taught here, is the product of square root of 4 times 76 over 5 a rational number? Explain why or why not. Okay? So is the product of square root of 4 times 76 over 5 a rational number? Please explain why or why not. And put your answer in the chat. Yes. Okay, Carney says it is, yes it is, because rational times rational is rational. Yes, very good. Good job, Carney, and Stephen, and many others. Okay. Good job. So, yes, it is because irrational times irrational equals to a rational. Very good job. So now let's move on to the next problem. Which numbers are irrational numbers? Okay, select all that apply. Okay, I'll give you some time to try and solve this. Hey, and put your answers in the chat, please. Okay, which numbers are rational numbers? Select all that apply. I'll be looking for answers in the chat. Okay, so we have A and C. Those are the answers. Very good job. And Carney provided us with an explanation. So very good. A is pi, and that is obviously irrational, and C is an unending random decimal. Very good, Carney. And good job to everyone else that got it correct. So yes, very good. And lastly, thank you for listening. Okay, so this will be the end of our class. And thank you everyone for coming, and you were all very active in answering today. So very good job. Thank you for listening.